this is the chapter on electronic structure, which is the number of electrons in an atom and their distribution. So lesson 22 is a review of the atom. And what I'm going to do is post the PowerPoint for lesson 22 online because there are numerous links that I want you to watch in here. So remember wavelength and frequency. The wavelength of a wave is measured in nanometers or meters. And remember, it's the distance from the crest of a wave to the crest of a wave, or that's the same thing as the trough of a wave to a trough of the wave. And the frequency is how many cycles or waves per second pass a fixed spot, and that's measured in hertz or 1/seconds. And here's the electromagnetic spectrum, and remember, depending on the wavelength and the frequency of the energy, you get different types of waves. For example, visible waves, the light that we can see, is only the small portion of the electromagnetic spectrum. And remember that the speed of light, which is 3 × 10⁻⁸ meters per second, is equal to the frequency of the wave, v, times the wavelength of the wave, lambda. And so as wavelength increases, frequency must decrease. So here we have purple light, which is the shortest wavelength, but the highest frequency. And red light has the longest wavelength, but the lowest frequency. So energy can only be absorbed or released from atoms in chunks, and we call those chunks quanta. And a quantum is the smallest quantity of energy that can be emitted or absorbed as electromagnetic radiation. And the energy of that quantum is equal to Planck's constant, h, times the frequency of the radiation that's being absorbed or emitted. So here's an example showing that energy is quantized, meaning that this turtle, it's more like stairs. You either absorb or release a chunk of energy. It's not a gradual amount of energy. So here's an example of a problem you might encounter. Calculate the energy of 1 photon of yellow light that has a wavelength of 589 nanometers. So you know the wavelength, so you can find the frequency, and then from the frequency and Planck's constant, you can find the energy. Line spectra are used to identify different types of atoms. So for example, an absorption spectrum is when you hit a gas with white light, okay, and that gas will absorb some of that energy because those electrons will absorb energy and jump up in energy level. And so where it absorbs energy, where those quanta of energy are absorbed, there's lines missing from the absorption spectrum. And then if you apply energy to a gas, meaning that the electrons will jump up, eventually, remember, they have to fall back down to ground state, and so it will emit energy that has specific quanta or chunks based on which energy levels they're falling from. And you can see here that this is the emission spectrum of hydrogen, which these lines match up exactly with the absorption spectrum. So whatever they jumped up, they also fall down in terms of quanta. And the Rydberg equation can be used to calculate the wavelengths of those lines that are being emitted. So Bohr, remember, said that electrons orbit around the nucleus. But the question about Bohr is, why don't they just lose energy and spiral down into the nucleus? And Bohr assumed 3 things when he came up with his model. He decided that only orbits of certain energy are permitted in hydrogen. And the second assumption is that electrons in an orbital are in an allowed energy state. So they don't give off energy and they do not fall inwards. And the last thing he assumed is that electrons can jump from orbit to orbit by absorbing or emitting photons. However, Bohr's model does not explain anything but the line spectrum for hydrogen, not other atoms. And he basically just assumed that electrons would not fall into the nucleus. And finally, electrons are not just orbiting negative particles. They actually have wave-like light properties. And so his model was important because it said that electrons only exist in certain energy levels. And it is also important because it said that energy was involved in the transition from electrons jumping from one orbit to another. So those were new in their time. However, like we said, Bohr's model does have some limitations. De Broglie, however, came up with the theory that an electron behaves like a wave, and so it has a wavelength, and you can find the wavelength of an electron by dividing Planck's constant h by the momentum of the electron. And these wavelength properties were actually proven experimentally. So here's just a short joke for you. And Heisenberg, remember, has his uncertainty principle, which says that because matter is both particle-like and wavelength, we cannot know both the location and the momentum of an object at any one time. Schrödinger came up with some equations that include both wave and particle-like behavior of electrons. And so because of the uncertainty principle, we can only talk about the probability that an electron is in a region. We can never absolutely be sure.